my topic of research is probabilistic geotechnical site characterization. Why is soil characterization important for us? Because every construction procedure involves a sound foundation on which it is built. So the stability of a structure depends on how good we know about the soil, how good we characterize the soil. And hence the topic is this. So today's presentation, I'll outline my motivation, I'll go for my problem statement, then I'll discuss the various stages, how I attain my results. Okay, so I start by stating that soil is highly heterogeneous. By heterogeneity, I mean it consists of non-uniform layers. As you can see in this diagram, there are a number of the layers are not uniform. Also, it consists of discontinuities which we call lenses. So these lenses and this non-uniform layers form a very complex correlation structure which we need to characterize. But for accurate characterization of this, even if deterministically or probabilistically, we need a very large amount of data. But the existing site characterization techniques, the data that we get is not always enough. Why? Because we have a conventional borehole approach where we go to the soil deposit, we go to our site, we dig holes, collect samples, do some laboratory test, or maybe we do some in situ test. However, this approach is mostly based on intuition, and also we sample at a very few locations. This is because of inaccessibility of the site. This might be due to cost. This might also be due to the underlying soil media, which is impenetrable. Sometimes what engineers do is they go for kriging or random field sampling, but it suffers from a lot of bias due to the unlimited data that we have. There is also something called as the geophysical approach, in which we have, this is a non-intrusive process in general, compared to obviously the borehole approach. What we do is we have a wave creating source on the surface of the soil. There are sensors located at a few spatial locations. So what the sensors do is they measure the wave that propagates through the soil, several properties of the soil, of the waves. What this does is it produces a large volume of data because this is fairly inexpensive. The measurements, they contain more information. This is because the waves travel through all these non-uniform layers, they travel through all the lenses, and hence they get reflected, and hence they contain a lot more information. So certain analysis techniques are spectral analysis of surface waves. It's a fairly it's the current state of practice. But the assumption here is that soil is a homogeneous. It consists of homogeneous layers, which is not exactly right, and moreover, it produces only the vertical soil profiles. Something recently has been developed. It's called full waveform inversion. What this kind of produces a three-dimensional heterogeneous high fidelity image for the soil. However, it fails to account for this intrinsic uncertainty that might occur due to the measurement uncertainty, that might occur due to the spatial uncertainty, the spatial variability of the soil. Our approach would be a stochastic PD constraint stochastic waveform inversion of the geophysical measurements. What this process would do is it produces a high fidelity image of the soil. Also, it helps in the uncertainty quantification. So these are the various outline of my whole process. So we have a forward problem in which the target parameter is discretized by some underlying maths. Then we run a stochastic collocation approach. We run it through a finite element model, which is a PD-based model response. We have our two data from the sites. However, not for this experiment. We just go for a fixes geophysical experiment. We fuse them in a data fusion unit where we invert the results. We have some error minimizing process, and then we calculate the posterior statistics of this uncertain parameter theta. We calculate the posterior distribution and again invert the entire process. This goes on till the error is sufficiently minimized. my problem statement is that I would probe this 200 cross 200 cross 45 meter soil domain. The Young's modulus is an anisotropic random field. This is my target parameter. Poisson's ratio is assumed to be constant and it is deterministic. All other assumptions are based on what are concurrent with the real field, what actually exists in soil equations. I'll start by my first step, that would be the forward problem. The forward problem has 3 steps. The finite element model for providing parametric values for finite element model, we need to discretize the 3-dimensional heterogeneous random field. That's our Young's modulus, and then we propagate the uncertainty. We quantify the uncertainty using the stochastic collocation approach. For finite element, we just use the 8-noded standard brick element. Since soil is a part of an infinite half space, we just probe a small domain of it. We have to use artificial absorbing boundary conditions. We also go for chirp signal because we want to see the response of the soil to a wide range of frequencies. As you can see, it ranges from 3 to 10 hertz, the frequency that we use for probing. Now we go for discretization of the 3-dimensional random field. The challenges are that we need a few random variables, random parameters to discretize the whole soil domain. That's because otherwise the problem would be huge, it will be intractable. There is something, the KL expansion has, we know that KL expansion is more or less, it requires, we need prior assumption on the correlation structure for the soil. However, it's very difficult to actually predetermine what the correlation structure of the soil, because the data that exists is very, very limited. Also, the number of random variables for a KL expansion is too large, because it consists of eigenvalues, and for any kind of accurate estimation, the number of random variables become too large. Our strategy would be a Gaussian mixture model. A Gaussian mixture model is we represent our random field in terms of Gaussian shape functions and Gaussian weights. These are the weights. This is the Gaussian shape function. So we are representing the entire random field in terms of 5 parameters, which we need to calculate in our inverse this entire inverse process. So what we have attained is we have represented the entire random field, the entire 3-dimensionally heterogeneous random field in terms of just 5 random variables. So this approach is quite elegant. It's really, as you can see, these are 4 realizations of the of our process of the random field. As you can see, it can also produce uniform layers, which we see in some soils. It produces these lenses, and it can also produce crazy heterogeneity also. So I believe that this method is quite powerful in actually generating something which is close to the real soil structure. For uncertain propagation, we go for a stochastic collocation approach. What we do is we just need to find a process to find this integration for calculating our posterior or prior movements. We have Monte Carlo simulation, however, it's very slow in converging. We need, and it's computationally too expensive for our 3D soil domain. We have Gaussian quadrature. Again, for higher dimension, it becomes too computationally expensive. In literature, we have more like a sparse grid and uncertain transform. However, these methods, they fail to give accurate results due to these negative weights in higher dimensions and higher orders. Hence, we went for a recently developed method called conjugated uncertain transform. As you can see, the results, this is for Clensor-Cortez, and for Gauss-Legendre, it produces much lesser points as compared to all these other pre-existing or traditional methods. Hence, so the acceleration is a function of y. Acceleration is what the sensors measure at the locations. we say that we need 425 cut points for getting accurate results up to sixth order movements. So we generate 425 realizations of Y. Since we don't, we are targeting a fixed geotechnical site. We assume that this is our true value, and we will try to invert the results so that we achieve this true value. These are the measurements of acceleration at the different sensor locations. This is the mean, this is the standard deviation, and this is the spectra. Okay, for the inversion process, we go for the minimum variance framework. For a sensor model, Y, where h of theta is the true measurement, mu is the measurement error. The first and second order movements are given by these two formulas, where K is the Kalman-Gain matrix, and it is a measure of how much information this measurement Y has given us. As you can see, K is proportional to this parameter sigma theta Y, which is basically a covariance between theta, which is our unknown random parameter, and Y, which is the measurements. All expectations, as I mentioned before, are calculated by the cut approach. This is one example of how I calculated the expectation, this integration for sigma theta Y. Results. We got some interesting results by this, even after just one inversion stage. This was the prior mean and the prior standard deviation. As you can see, the true value and the posterior mean almost converge, and the error is very less. Error as in the standard deviation. This is the true value minus the prior value. So this was what we started with. This is what we got after our inversion results, which is almost zero. The error is almost zero. And this is the amount of knowledge we gained from one inversion process, which is fairly large. We also conducted a study on how much information gain or where can we, this is a very preliminary study on where we can place our sensors, which will give us a good information about the whole soil. This is the number of time steps that we took into our inversion process, and this is the number of sensors that we use. This result is fairly obvious because the error decreases as we increase the number of sensors and as we increase the number of time steps. However, these results were quite interesting. As you can see, only the top surface, the sensor located at the top surface give us the maximum information gain. The dark blue region is the region which has the highest information gain, and we say that we don't, this can lead to a conclusion that we need just to put the sensors on the surface of the soil instead of digging deep. The conclusions, this is fairly a mathematically robust methodology. We were able to produce high fidelity image of the soil. We did some uncertainty quantification, and this method was computationally very expensive because, let me just put it into perspective. A single run of our model takes 24 hours. If we had gone for Monte Carlo, it would have taken us 6 years with 425 parallel processors. Even if we had gone for Gauss quadrature, it would have taken us 7 months with 425 parallel processors. However, this just took us 3.5 days with 425 parallel processors. So we decreased a lot of the computational load. For future work, we are working on validation with real field measurements. We want to estimate additional soil properties, including elastic plastic soil parameters. This can be achieved just by adding a few more parameters because our parameters is just 5 till now, and which is very less, which is computationally tractable. We are also working on how to develop a maths to actually get a robust methodology to actually optimize our sensor locations. That's all. Thank you.